Okay, now we move on to chapters 17, 18, and 19. We look at analysis and the basic analytical techniques. These 4 dot points below are what was covered and what will also be covered in the examination. So you can just have a quick look at them. Actually, colorimetry is something we've done in class, but we are not going to be testing that in the year-end examination. Okay, just AAS, titrations, and gravimetric analysis, and HPLC as well, which I'll cover later. Please have a read of question 1. Basically, it is an atomic absorption spectrometer, and you measuring standards to determine the calibration curve, and then from the calibration curve, if we run a sample, we can determine what the concentration of the sample is. Okay. I found that some students really have a problem of plotting of graphs. Okay, I just want to explain how I go about plotting this graph. Okay, firstly I look at the data table given. Now the data table gives me information on absorbance and concentration. So to get the concentration scale right, I know that's going up 2, 4, 6 ppm for the x-axis. That is pretty straightforward. I know how to do 2, 4 and 6. That's easy, right? But looking at the y-axis on absorbance, I've got some numbers there which are decimal numbers. It might be difficult to draw something like this. Now I'll look at the range of my y-axis. I notice that my first value is 0.12 and my last value is 0.200 and something. Okay, so how can I set up my system of axes? Okay, the red lines I've got on the y-axis is the actual graduation lines. Now I can just try numbers, so I ignore the decimals. I look at numbers like, in this case I've got 40, 80, 120, 160, 200, 240. It's going up in units of 40, and you can see with that scale I cover the entire range that I need, and I can then just plot my values, so it is not as complicated as it looks. Okay, suppose I started every graduation, the first one, instead of it being 0.040, I had it as 0.010. If I count up, you see I will not have enough numbers to cover the entire range of absorbances. Okay, so if I went, maybe try 20, 40, 60, 80, or I could try, if I started higher, if I was at 50 or 60, you'll notice that it couldn't, and it's only the 0.40 for, in my case, that works out well. So that's how I go about doing it. So it doesn't take a long time. It can take some trial and error. So I suggest when you're drawing graphs, it's good to start with a pencil first and work from there. Okay. Now the next step is just to plot the value according to the table. I know that 2 ppm is close to 0.080. The 4 ppm is close to the 0.160, etc. And to work out my unknown concentration, which is 0.172, it's obviously going to be 172 is greater than 160. That's why it's going to be slightly above. And if you follow my gray line there, and I bring it down to the x-axis, I get 4.5 ppm as my answer for the unknown solution. Okay, now question 1b asks us to find the molar concentration of potassium. I know the concentration is 4.5 ppm. ppm is milligrams per liter. So let's work with the mass only. So what we're saying, in 1 liter there's 4.5 milligrams of potassium. To work out the molar concentration, I need number of moles over volume. Okay, so my volume is 1 liter. To get number of moles, I have mass, okay, which is 4.5 milligrams. I need to convert mass to moles. All I need is the molar mass, and the molar mass of potassium, mK, is equal to 39.1 grams per mole, and NK is the number of moles of potassium, which is my given mass, which is 4.5 milligrams. You can see I got 4.5 times 10 to the minus 3 grams. Because I'm converting milligrams to grams, I have to divide by 1000, and then I divide that by the molar mass, 39.1. I get a certain number of moles, and now to calculate the molar concentration, I take that number of moles and I divide it by my volume, which is 1 liter in this case, and I get a concentration or a molar concentration of potassium of 1.151 molar. Right, I suggest you just pause this video at this point, try and walk through this and understand how it works. Okay, the next topic we look at is HPLC. HPLC, you need to know what RT is. RT is retention time, and that's the time it takes for a component to pass through the column. If you find this a bit confusing, you'll need to go back to your textbook and have a read of that. Okay, looking at question 3. The detector response is 0.40 and the height of the peak is 12 centimeters for component A. What will be the detector response and peak height of component A if the component A's concentration is increased from 200 to 300 ppm? So obviously if we have a stronger concentration, we're going to have a higher peak, or a peak more than 12 centimeters. Right? So if it's going to be more than 12 centimeters, we have to take the higher concentration divided by the smaller concentration. So 300 ppm over 200 ppm, that gives me a factor of 1.5. So my peak height is actually going to be 12 centimeters times 1.5 is 18 centimeters. And the absorbance reading also going to go up by the same factor of 0.40 times 1.5, giving me 0.60.